move on to an extremely important topic, type classes. Before I show you exactly what they are, let's consider the motivation behind them. Suppose we create our own data type called myBool with two data constructors, t and f, representing true and false respectively. We are using these names to avoid clashing with the inbuilt ones which are already part of the Haskell prelude. Now suppose that we want to write a function which shows a string representation of a myBool instance, which we will call showMyBool. The type signature of showMyBool would be myBool to string, and the implementation is quite simple. We provide two bindings for the function, one for each possible value in the pattern match, and return true if the value is t and false if the value is f. And the function works as we would expect. Now suppose we create another data type for representing certain errors which can occur in our program, and we want a function which shows us a string representation of the data type. So we write our function called showMyError that gives us a string representation for each of the potential values. There is nothing complicated here, we just use pattern matching to match on each constructor and return the description of the error as a string. And it works just as we would expect. Now, it is quite annoying to have to use a function with a different name for each type. Is there a way to generalize the ability to generate a string representation of a type to avoid this? At first, you might think, okay, maybe we can write a function which takes in any type and returns a string. In other languages, you can actually inspect the type of a value at runtime. But in Haskell, this is not possible. There is no way we can know what the caller of the function has decided to use as the type of the parameter at runtime, because at compile time, all we know is that it is of type A, and at runtime, there is no type information we can query. With this function signature, we must write our code for the most generic situation possible, and so it is not possible to write a function with this type signature and specialize it to act differently when the type of parameter is a myBool or a myError. But Haskell offers us another way of expressing that a type should be able to support a specific behavior, and that is through type classes. Type classes provide a structured way to introduce overloaded functions. We'll see what this means concretely in a minute, but in simple terms, function overloading is the ability to create multiple functions of the same name with different implementations depending on the types. That sounds like exactly what we need to define a generic myShow function. Let's use type classes to do that. There are two key concepts you need to understand when it comes to type classes. The first concept is the type class definition. The generic template for defining a type class is as follows. And here is our definition of the myShow type class. Let's take some time to understand what exactly we are doing here. You use the class keyword to declare a new type class. This is followed by the name of the type class which you want. In our case, we are defining our myShow type class. Then there is a type parameter which we conventionally call A. Then the where keyword, followed by a list of function signatures which can be overloaded. You can put as many function signatures as you want, but for our example, we are just putting one. Notice how the function signature is the same as the generic one we tried to define earlier. Now the second part of type classes is actually defining the overloaded functions. This is known as defining the instance for a type, and is done as follows. Here, the syntax is similar to the type class syntax we see above. We begin with the keyword instance instead of class, and then give the name of the type class followed by a value for the type parameter. In this case, the value is the myBool type. Then we have the where keyword, and in the where block below, we provide an implementation of the function specified in the type class. In our case, the only function specified in the type class is myShow. However, since we have provided the value of myBool for the type parameter A in our instance declaration, it is as if the function we are implementing has the type signature of myBool to string, and so we can implement the function just as we implemented our showMyBool function. You can see that the actual implementations here are identical, and we can create our instance for the myError type too. Just like before, it follows the same pattern. In this case, since the value given to the type parameter is myError, you can think of the function implementation in the where block having the type signature of myError to string. And so we can provide the overloaded function definition which matches the exact same definition of the showMyError function which we defined before. You should note that the class and instance declarations follow the same whitespace rules we have gotten used to. After the where keyword, you should indent each line by the same amount of spaces, like you can see on the slide. What exactly does defining the myShow type class and also defining the myBool and myError instances for the type class give us? We can see what it gives us immediately by asking GHCI for the type of the myShow function, which is specified in the type class. If we do that, we get back a function signature like this, which contains a new notation. Just like before, we have the name of the function, which is myShow, followed by a double colon. But now we have the name of the type class myShow as well as the type parameter a, and then a different type of arrow symbol than we are used to. Then we have the actual type signature we specified in the type class definition. We call this new type of arrow a fat arrow, as opposed to the other thin arrow which we have already been using in our type signatures. Essentially, everything that comes between the double colon and the fat arrow is what we call a type class constraint. Sometimes it is called a type class restriction. We would read our generic myShow function signature as a function which takes in any type and returns a string. But with a type class constraint, we read this as a function which takes in any type which has an instance of the myShow type class and returns a string. Effectively, we are constraining the type parameter a to only belong to those types which have an instance for the myShow type class. This restriction means that we know that the type of the parameter passed in will have an overloaded definition of the myShow function which can be called. By having this type class constraint, we are able to overcome the problems associated with the generic myShow function, and whereas before we had to define a function with a different name for each different type, we are now able to just call the function with the same name, myShow, to get our results, which is much tidier. And when we do that, everything works fine, as you can see. But then what happens when we call it with another type? Let's suppose we call myShow with the value of true, which means we are calling it with the value of type bool. Well, we get an error, and this error occurs because Haskell cannot find any instance for the myShow type class for the bool type. We could get rid of this error by providing an instance of myShow bool, which would look very similar to our instance declaration for myBool. The good thing about this type of error is that it is picked up at compile time rather than at runtime, so you will have to fix it for you to even run your code. That's a lot we have covered in one slide, so let's summarize. A type class defines a set of function signatures that instances of the type class must implement. Within an instance declaration, the type parameter, which we conventionally call a, can be thought of as being filled with the concrete type given. So, for example, the type parameter a is given the value of myBool in the myBool instance declaration and the value of myError in the myError instance declaration. You can use type class constraints in your function signatures to restrict the type parameters to only be from those types which have instances of the specified type class. You can, if you need to, have more than one type parameter in a type class if you use a Haskell extension, but that is beyond the scope of this course, and we are only going to be looking at type classes with a single parameter. There is actually a type class predefined within Haskell called show that does exactly what our myShow type class does. The show type class is used everywhere, and we will look at it in more detail later. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the Learn channel. See you next time.